When a capacitor is placed in a circuit, the battery's EMF causes negative charges in the form of electrons to flow from one plate to the other, creating a potential difference across the oppositely charged plates. And these negative charges flow back when the capacitor discharges. If two capacitors are in parallel, there are two separate branches of the circuit that can charge and discharge. This allows for more total charge to be stored by the capacitor combination compared to a single capacitor with the same capacitance. For the two capacitors shown here in parallel, I have assigned them capacitance values C1 and C2. Now for any circuit elements that are in parallel, the potential differences across them are the same. So for capacitors in parallel, they're each going to store the same potential difference. However, in parallel, current is split. Now current's the flow rate of charge, so any charge flowing in to the node here has to be split. Some of it will go to capacitor 1, I'll call that Q1. The rest will go to capacitor 2, which I'll call Q2. And then conservation of charge says that the total charge is just the sum of those two charges. The charge stored in a capacitor is given by charge equals capacitance times voltage. So I can use this to solve for something called CEQ, which is the equivalent capacitance, which gives the total charge on the capacitors as if they were one capacitor. So for the whole circuit here, the total charge is the total capacitance, CEQ, times the total voltage, which is given by the battery. That's going to equal the charge on capacitor 1, which is C1 times its voltage, which is the full battery voltage, plus C2 times the voltage there, which again is the same. Here the voltages cancel out, and I get that for capacitors in parallel, the equivalent capacitance is found by just adding up the individual capacitances. Here it's just C1 plus C2 because there's two capacitors, but this works for any number of capacitors in parallel. The capacitances just add together. So overall for capacitors in parallel, the capacitances added up, the charges stored on them add up, and then they store the same potential difference across their plates. All right, example A looks at two capacitors in parallel, and it asks to find the charge Q on each capacitor, which is given by CV. So they're both in parallel, so they both get the 12 volts given by the battery. For the capacitor on the left, which I'll call capacitor 1, its charge is 6 times 12, so it stores 72 coulombs of charge. Q2 on the right stores 144 coulombs of charge. When two capacitors are placed in series, negative charges from one plate of a capacitor travel to a plate on the other capacitor, while the area between the capacitors is not actually connected to the rest of the circuit, since charge can't flow directly through a capacitor. However, the capacitor plates still acquire opposite charges since the area between the capacitors will polarize. For capacitors in series, negative charges from a plate of one capacitor flow to a plate on the other capacitor, and then the area between the capacitors polarize. Now for a series circuit, current, which is the flow rate of charge, is the same. So for capacitors in series, they're each going to store the same charge Q. However, in series, the potential differences are going to be different. So the battery voltage here is V. Capacitor 1 will have a potential difference of V1, and then capacitor 2 will have V2. So in series, the potential differences of the individual circuit elements add up to the total potential difference. And then I'm going to use the fact that potential difference across a capacitor is the charge stored in it over its capacitance to determine an expression for CEQ, or the equivalent capacitance, in series. So the total voltage of the power source is the charge stored in both capacitors, Q, over the equivalent capacitance, and that equals the sum of the potential differences across the two, which will be Q over C1, plus the same charge, Q over C2, and then the Q's here cancel out, and I get that 1 over the equivalent capacitance equals 1 over C1 plus 1 over C2. And again, this will work for any number of capacitors in series. What this ultimately means is that in series, the equivalent capacitance will be less than any individual capacitor's capacitance. The potential difference in series adds together, and then also in series, the charge stored on each capacitor is the same. Example B looks at two capacitors in series. It's the same two capacitors from example A, but now wired in series. So for this one, to find the charge on each one, both charges are the same. So to find the total charge, I'm going to find the equivalent capacitance times the battery voltage. So to find the equivalent capacitance, I'm going to say 1 over equivalent capacitance is 1 over 6 plus 1 over 12, which would be 3 over 12. So the equivalent capacitance is then 4 farads. And then to find the total charge, the charge is 4 farads times the battery voltage of 12. And I get that there's 48 coulombs, and that's going to be on each capacitor. Now in this case, these are the same two capacitors as example A, but each capacitor stores 48 coulombs. That's in contrast to example A, where the 6 farad capacitor stored 72 and the 12 farad capacitor stored 144. So when the capacitors are in series, they're going to store a lot less charge than they did in parallel. The last question here, example C, gives a capacitor combination. B and C are in parallel with each other, and that combination is in series with capacitor A. All the capacitors have a capacitance of 12 farads, and they're connected to a 12-volt battery. So I want to combine all the capacitors together to get a total equivalent capacitance. I'll start by combining B and C in parallel. In parallel, the capacitances add, so they have a total capacitance of 24 farads. And then for the 12 farads from A and this combination, I'm going to find the combination there. So 1 over the equivalent capacitance is 1 over 12 plus 1 over 24, since those two are in series. That's going to give 1 over 8. So the equivalent capacitance is 8 farads. So to find the total charge, I use Q equals CV. 8 times 12 gives 96 coulombs. So there's 96 coulombs of charge stored here. I'm going to go back to the original circuit. But first I'll go back to step 2. Here, the 12 and the 24 are in series. In series, current's the same, so charge is the same. So they each have 96 coulombs of charge, which means capacitor A then has 96 coulombs of charge. Now this doesn't give me the charge for B and C. I do know their total capacitance is 24 farads. So to find the voltage on each one, I'm going to find the equivalent voltage. So from Q equals CV, voltage is going to be charge over capacitance. For B and C, the total charge, not the charge for each one, is 96, and the total capacitance for those two is 24. So both B and C are going to store 4 volts of potential difference. To find the charge on each one, either B or C, it's going to be Q equals CV. They both have the same capacitance of 12, voltage of 4, and I get that each of them is going to have 48 coulombs of charge. Now that does match up with step 2 here. In parallel, the charges add, and then 48 plus 48 is 96.